Hello, everyone, and welcome to Pi Data Trinidad and Tobago. My name is Torian Dyer, and I'll be your host for this evening. Today, we have Olusanya Todd with his talk on deploying machine learning to the very edge. As always, with our Pi Data talks, we have a code of conduct where we ask you to be respectful, to not put down others, to be considerate, and just have a great time. We're going to have fun discussions at the end of this talk on some of the implications and use cases on what Olusanya will be talking today. So right now, and I'll let Olusanya introduce himself. I give you Olusanya Todd and his talk on deploying machine learning to the very edge. Take it away.
All right, good morning, everyone. So as Torian very well introduced, today the talk is going to be on deploying machine learning to the very edge. And so today we're going to be covering, very briefly, we'll cover a demo. We're going to cover who is Olusanya. Then we'll follow into a brief introduction into microcontrollers and machine learning with them. And then TensorFlow Micro. And finally, the meat and potatoes, our own research and what we've introduced to the table. And we'll finish it off with a tutorial on showing how you can do it yourself. So the demo. Now, I don't really like light switches. I like to spin things. So I made this device. And what we have here is a breadboard. We have an ESP32. It's currently connected to my laptop. And this is an accelerometer. And so when I do this gesture, when I rotate counterclockwise, the light should turn off. Right? And when I rotate clockwise, the light should turn on. Okay, so that's just a quick.
With it in camera.
Oh, it wasn't in camera. Sorry, my bad. Okay, so when I rotate counterclockwise, right, it should turn off, and when I rotate clockwise, it should turn on. Okay, you all saw that, right? So that's a quick demonstration of what exactly we're going to be covering today. And yeah, let's get into it. So before we really get into the talk and the machine learning and all that, I just want to go over who am I? Who is Olusanya Todd? And so I am an 18-year-old QRC student. For those of you who are living away, that's a school here in Trinidad. And I am just about to graduate, actually. So yeah, one thing about me is that I am addicted to learning and understanding STEM. So I love technology, just anything I can get my hands on that I'm curious about, I would find myself researching for hours, whether it's SQL and database designing or game development, right? And so I found myself in a lot of very wide-ranging and varying areas and interests, just kind of not sure exactly what I'm going to get into. And very recently with Torian, I realized that robotics is where I want to find that blend and problem solving so I can draw from all these different interests and inspirations. So yeah, that's a little bit about me. And I just want to touch on how exactly did I end up here talking to all you very esteemed gentlemen and gentle ladies. So 2 years ago, actually, I attended Next Gen Coding Camp, where they brought a lot of Trinidadian, very successful people in the technology industry, and they brought them to mentor and talk to us. One of which was actually Mark Moyo, who to this day still assists me in mentoring and different areas. And so from there, that was one of the key moments where I realized this is what I want to do. I love technology. This is where I want to go. And the following summer, I actually held my own robotics camp to teach kids who were like me, you know, that they have this interest in robots and building things, but they just don't really know where to go or where to even begin trying to make something and create something. And yeah, from there, I met Torian actually, and we've just been working on a whole lot of stuff. One thing we did was we developed open source telepresence for Waterfall robots and presented it to the NVIDIA VP, Claire Delancey. She's the inventor of the Waterfall. somewhere in the middle there, I launched my business, The Mill, a local apparel e-marketplace for teens who don't have credit cards available to them. And then now currently, and the reason I'm here is I've been working with Torian in AR and VR with HoloLens and Magic Leap, AI, robotics projects, and also helping local startups. So yes, that is who I am. And let's get into it. So what is a microcontroller? A microcontroller is a programmable chip that is used to manage connected input and output devices. Essentially, you can think of it as a mini computer. And we can see in the diagram here a few of the comparisons, right? So we have a standard computer, a lot of dollar signs there, and that's in order of magnitude, right? So it'll be a lot more expensive than our very cheap microcontroller. But on one hand, the standard computer can do many tasks at once. It can play your favorite game, music in the background while you're watching a YouTube video and doing your schoolwork or whatever, whereas the microcontroller can typically only do like one task at a time. We also have the midpoint where it's a single board computer, for example, the Raspberry Pi. So there's really a spectrum of computing power, affordability, size, and all these things. But one of the key points, I think, is specifically to machine learning, is that the microcontroller, it's extremely difficult to train on and build models on the microcontroller itself. Whereas the standard computer, you can, it's easy to train, you can make inferences quickly, etc. But it's very difficult to do that on the microcontroller. And so today we're going to be seeing how can we work around this and actually solve machine learning problems on the microcontrollers that are so affordable. So just some examples of where you can find these devices, microcontrollers, right? And they are literally everywhere, from robots to coffee makers. You can see some examples of drones, Alexa, coffee maker. They are found in many devices in your home right now. Okay. So let's look at the history and what came before, and how exactly was machine learning deployed to these microcontrollers before TinyML and TFMicro, right? Which are the modern day solutions. So what came before? And there was the do-it-yourself method, essentially. Because standard high-level machine learning libraries couldn't be used on low-level microcontrollers. And what I mean by that is NumPy, Pandas, these large libraries, microcontrollers don't typically have the computing power to run those libraries. And so algorithms actually have to be implemented from scratch in the native language, whether it be Python on your your Pico or Arduino on other microcontroller devices, right? So it has its flaws. It's time consuming, errors are harder to diagnose, and it requires very deep, specific microcontroller knowledge, okay? Now, there are some recent notable solutions. For example, Raspberry Pi, they have dedicated libraries and standard libraries, but of course, that is a single board computer and not a microcontroller. We also have dev kits, dedicated dev kits, such as Google's Coral Dev Board, the OpenMV, and NVIDIA's Jetson series. And we also have dedicated libraries like Microsoft's EdgeML. All of these are currently working on doing machine learning on microcontrollers, but they are limited to specific boards and coprocessors. So what does TinyML allow us to do? Well, there are many capabilities, but the main thing is that TinyML ports TensorFlow Lite to Arduino code. It allows for quick development of machine learning apps, and they have an aesthetic, intuitive front end with extensions. And well, it's easy to use. But there is another flaw. It's only built for the Arduino Nano BLE. And so the question today that we're going to answer is, can we port this to other Arduino programmable microcontrollers for example, microbit, ESP boards, and many more. Now, before we look at how exactly we can do that, why should we extend TinyML to these other MCUs? And the main advantage is cost and capability. The SP32 is a cheaper, more capable board. It's less than $6 US per board, has an arm sensor, Wi-Fi, Bluetooth Low Energy, and a lot of input-output options. You can also do image and video capturing. It's used in many commercial Internet of Things products like Twinkly, Goal Zero, Yetis, lights, and more. So it's cheaper and a lot more capable. And finally, the meat and potatoes of the mix. How are you going to be doing it? So here we're getting into the code, and I just want to put out a disclaimer. These first few slides we might go through kind of quickly because it is a generic TensorFlow setup. So if you know how to build a neural network in Python using TensorFlow, you'll be quite set, quite comfortable. If not, there's a lot of information online on YouTube on how to do these steps, but we still go through it anyways. So we can see at the start here, the first thing we do is we import our libraries. So we import pandas, sklearn, glob, os, etc. And then after that, we set up some input configuration variables. Now, these are very specific to our use case using gesture recognition, right? Because we are using MPUs and we have like you can see num readings per sample per MPU and number of MPUs. These are specific to our use case. But let's say you wanted to use a humidity sensor and run some machine learning program on that, or a light sensor or whatever else. Your input, how you're going to configure that information is going to change, right? But for our case, these are the configuration input variables that we use, okay? And then the next notable thing is our gesture index. And we can see we started off as 0, and that's just the output label we're going to use for our neural network gestures. So as we train a new gesture, let's say we had the clockwise and then the counterclockwise, we're just going to label those as 0, 1, 2, 3 in the output layer afterwards. Right. The importation. So in this step, we are going to import our data, right? So at the top here, we can see we reference our previous variables. We bring in our gesture index, our input configuration and all that. And then we read our CSV and save it in our gesture CSV variable. So this is assuming that in collecting your data, you stored it in a CSV table, and that's what we did. And so we're gonna bring it into Python using pandas read CSV, and then we're setting up our input matrices for our data, right? We can fill them with zeros, as you can see under gesture X and temp X. Following that, we loop through our input matrices, and that's where we just copy in our CSV data. And all of this is just formatting. And of course, I repeat, it depends on how you recorded your data, how you plan on flattening that input layer and all that. Yes, Torian.
So where exactly are you getting your input data from? Like the microcontroller connects to something to do that, right?
Right. Yes. So, okay. So we're getting our input data from an app on the ESP32 itself that we developed. And you just...
How would you get the data itself?
How would you get the data itself? So when we get into the Arduino side of things, I'll show you, but we can, very briefly, we can read the readings, the MPU readings from our accelerometer, store that, actually send it back to our computer, And then from there, we have a program to save it and download the CSV, okay? So, right, so we have our CSV data, we bring it into Python, we reformat the input information, and now we're ready to go on and set up our final input and output matrices, okay? So we can see here at the top, we have our gesture Y, and this is our input layer. This is our input vector, okay? And we're just doing a full vector that is the size of the number of samples we have, and it's all full of the gesture index. So it's basically labeling every single sample we just imported as, okay, this is gesture 0. And then as we increment, it'll be, okay, all these samples of gesture 1, etc., etc., etc. And then what we're doing is we're going to bring all of these specific gesture input and output matrices. We're going to combine them and concatenate them into our final X and Y training data, okay? So that's what this function does. If gesture index equals 0, that is, if it's our first gesture, we're going to copy that information. And if not, then we're just going to concatenate that, and we're going to keep building our training info into the final X and Y matrices. And we can see at the end there, once we do that for our current gesture, we increment it by 1, and we repeat the process if we have more gestures. Okay, so right, the fun stuff. This is where we actually build the model. So we can see we import TensorFlow's sequential model, and their dense layers, they flatten, etc. These are standard TensorFlow stuff, right? And lower down is the important part where we see model.add flatten, and this is where we're actually creating the model. So we have one flattened input layer, and then a densely connected output layer. And we build the model, we do our evaluation, etc., and we see the accuracy. And here, there is room for improvement here. I did a very simple model. I'm not, too well versed in designing neural networks, etc. So this is where it can very much be optimized and improved upon, right? But once you get this basic fundamentals on how to get a model onto the ESP32, you can go crazy and make it really good, right? So moving on, this is the really, really key part that makes it able to go onto the ESP32. So what we have to do is condense our model that we just created, our TensorFlow model, so that it can fit on our ESP32. And to do that, TensorFlow Lite provides a converter that quantizes it. And what that does is it makes it smaller, but it loses a little bit of accuracy, which is a trade-off we have to take in order for it to actually work, right? So once we do that, we can see we use converter, convert TF Lite, etc., and then we use converter.convert, and that's running through and quantizing everything, making it smaller. And then we save our model. And finally, once we have it saved, the last step is just converting it to C code so that the ESP32 can understand it. And right, so that's using the TinyML gen library and their port function. Okay. So right, so that's it for the Python code. And now we're going to move into the Arduino side of things and how to code up a program to start running your predictions. So a quick disclaimer, we are using the Arduino IDE for this and coding in Arduino, etc. So you do need a little prerequisite knowledge as to how Arduino works, the basics such as their setup function, their loop function. But once you grasp that, the rest of this tutorial is really, really easy to follow. And so, yeah, we're going to go ahead into it. So at the top here, we can see we include some libraries, and these are just MPU libraries that allow us to read the data from our accelerometer. And that's simple enough. And then after that, we include eloquent TinyML and eloquent TinyML TensorFlow. And this is what we're using to like implement our model that we just made and actually run those predictions. So those are the key libraries here. Lower down, we can see we include our model.h, and that's the C code file that we just made in the last step, right? That's the actual model. Lower down, we can see we have our MPU formatting variables, such as the threshold. This is just an average of the acceleration in all the directions. And so once you move it and it goes above that threshold, it's going to start picking up the gesture. And then some more capture variables such as capture delay, how many samples you're going to take, etc. Right? And finally, at the bottom there, a very key part is the labels. So that is a little bit easier to understand because we know our model is going to spit out like 0, 1, etc. We can use this array to map an index to a name or a label. So in this example here, we have gesture 0 as right and gesture 1 as left. But you can change that to whatever you want, and you can have how many ever you want depending on how large your output vector is. Continuing with the variables, we can see at the top here, we have some more variables. All of these are actually related specifically to gesture recognition. So we can see we have number of gestures, is capturing, capture allowed, etc. All of those we're going to use later on in our program, and we're just declaring them now so that they're available in all the sub functions and they're globally available, right? So we'll get into more detail as to what those are doing when we reach lower down. But we can see we also have near the bottom there, our configuration variables for sampling, such as delay between each sample, how many samples, how many inputs we have. These are things that you can tweak. You can tweak how fast you want it, how detailed you want the accelerometer data to be per sample, you know, how long you want that sample to be. There's a lot of playing around with you can do there. And then finally, we have our MPU output variables. So that's the accelerometer. It's an accelerometer and gyroscope. So it outputs acceleration in the X, Y, and Z, and the gyroscopic information in the X, Y, and Z. And we store those there so that we could access them later on. So right, we've officially declared all our variables, I believe. Wait, no, we have just a few more, right? And this is one of the key things we have to look at. So here we can see we initialize the TinyML model. If you look at the bottom, and this is where we specify the number of inputs, the number of outputs, and the tensor arena size. We're going to use this TF object later on to actually run the predictions. Okay, so this is a very key part. Okay, as per the input array you see there, and it says 120. That is, it's 120 because I'm using 2 MPUs at the point when I was using this example, I was using 2 MPUs and it was 60 readings per gesture. And so when you expanded that, you had like 120 inputs. But of course, again, depending on your application and how much information you're collecting and putting into that input layer, that number has to reflect that as well. Okay. Also, a little note, as per the tensor arena size, you might have to change that depending on your model. It's a memory buffer that we use for the model itself. And so if yours is larger, if yours is smaller, you might have to play around with that number in order to get it to work. Okay, so moving on, we have the actual setup. So this is the setup function in the Arduino. It's not much. You can see at the top here, we declare 2 pins as outputs. And so that can be whatever you want. In my case, I declare this blue LED as an output pin. And that's for later on when we are doing our gesture recognition. We can say, hey, I want to turn that light on, etc. We also begin the serial so we can read and write messages, and we also wait for our model to load before continuing our TF model. So the loop. At the beginning of the loop, we can see here we have message equals serial.read string until \n. And what we're doing is we're just reading any messages that might be sent in serial, and then we're going to compare it against different commands that we have pre-coded beforehand to respond appropriately. So the first command we have is set desired MPUs. And what this does is it begins an initialization sequence, so to speak, where the user selects which MPUs they want to use. That is, if you're using several in your gesture recognition, right? The next command we have is start detect. And we can see it starts listening to the MPUs for gestures. And well, after that, we have the end detect, which stops the listening for gestures. Finally, we have reset threshold, which it's used to reset the still state threshold, as I mentioned earlier. And so to do that, you send the command, you put it down, and it would take the average of the current acceleration in all the axes, and it would set that as the average. And so you can do that to calibrate before you start running your predictions. So yeah, moving on, we're going to look at exactly what we're going to do if capturing is allowed and the while capturing loop. So let's get into this part, right? So we see if we are allowed to capture, that is, if someone said, okay, start detecting, we're going to enter a loop that says, while we are not currently capturing gesture data, meaning it hasn't gone over the threshold as yet. So it's not listening for gesture. So while you're not doing that, check for whether or not there is a reading above the threshold. And we can see to the side here, this is the function. And what it's doing is it's going to take readings from the MPU. It's going to average them. You can see we sum all the values, we average them, and then we check whether or not it's above the threshold we defined earlier. If it is, it's going to set, if it is above the threshold, we can see back on the left-hand side, we print out gestures detected, we set is capturing to true, and we reset our number of readings and our is reading above threshold bool. Okay, so that function is going to loop until the gestures until the accelerometer data goes above the threshold, and then it's going to flip that is capturing and it's going to exit the loop. So that's how that works. And it's just going to constantly listen until it does detect movement greater than that threshold. Okay, so once it exits that loop, we're going to move on to this function here, where it's actually going to loop if it is capturing. And the first step we can see is it's going to fill the input layer with MPU data. We see that function fill tensor. And what it's doing is it's taking a reading from, as I said, AX, AY, AZ. That's the MPU data that we're reading and storing. And we're putting it into our input vector or input array that we defined at the top. And so what we're doing is we're just filling up this input array. And back on the left-hand side, if we have enough samples, if the number of readings is above the number of readings required for a sample, then it's going to continue with the rest of the code. But if not, this is capturing loop. It's just going to keep looping it. So as soon as we have read enough gesture data, it says, okay, you have a full sample. It's going to enter that if statement. And what is the first thing it's going to do? It's going to turn off is capturing and reset the number of readings taken. And then the first thing we do is we create an output array and make our prediction using the TF model. So this is where the prediction actually takes place. if you remember, we defined that TF object earlier. And so this is where once we've detected motion above the motion threshold, and we have enough samples, we're actually going to run our prediction, run it through the model and see what gestures is being done. Okay, so we run tf.predict and we output the winner gesture. And we can also get the confidence level from it if we provide our output array. And so we can see we run same tf.predict, we provide the input, we give the output, and then we read that confidence level from the output array. So that's pretty much it actually. We now have we now can make a prediction and we can use that in other parts of our application. So here we see we set a specific output pin to high depending on which gesture was detected, but you can use this in many different ways, many different fields with many different inputs and many different outputs. So that's it. And as I mentioned before, there are many uses, some of which are smarter greenhouse controls, battery-powered robots and drones, or solar or low-powered machine learning applications. And very quickly, I just want to conclude that now you should be able to train your own microcontrollers using TinyML. You should be able to understand where and why to use machine learning in microcontrollers. And you should have seen oh, sorry, there's a little typo there, but you should found challenges and future use cases for this capability. So thank you very much. I do want to thank my family and teachers. Of course, I wouldn't be here with any of their support. Also want to thank Torian Dyer, who has been my mentor for a little bit over the past year. I want to thank Chris Manoha, who has helped specifically with this project. And we are also working on a project to come. And of course, Mark Moyo, a next gen, who started this entire journey. Thank you, everyone. And now on to any questions.